Hi, I'm Connor Goodrow, and my presentation today is on reconfigurable intelligent surface optimization using deep learning. I will begin by describing the optimization problem and the technologies surrounding this problem, and then describe a deep learning solution to the problem. The antenna array is an antenna divided into a number of smaller antennas which, accounting for distance, will linearly contribute to the received signal. Each antenna can also impart its own phase shift, and power can be allocated to each antenna individually, allowing for the antenna array to create a large amount of signals from a single antenna. By changing phase and power, a signal sent to a certain destination can be strengthened through constructive interference and also reducing its strength in other directions. This is an enabling technology for 3G and 4G, and in simple systems has closed-form solutions. For practical purposes, though, beamforming must be integrated with the rest of the communication system and be able to account for changes in location. The final technology is the Reconfigurable Intelligent Surface, or RIS. It is a near-passive reflector whose surface is broken up into many elements, each able to impart a phase shift, which can be programmed. Its main utility is in extending a signal's reach both as a reflector and as a beamformer. So now we arrive at the problem. How do we configure the two beamformers to maximize the capacity of the channel? This problem is highly nonlinear, and it can take thousands of parameters to optimize, making machine learning techniques a good solution for this problem. The equation given is a function of the channel matrices, H and H, which incorporate path loss and travel time, as well as the tunable matrices G, which is the power of the beamformer, and phi, which is the phase shifts from the RIS. It should be noted that G is constrained by the transmit power, and phi is some discrete value, generally 0 and 180 degrees. My initial goal was to cover the algorithm I was planning on building for a competition where, given a set of RAS configurations and received signals, we were supposed to find the optimal beamforming configuration. What I discovered as I worked on this problem, though, was that the machine learning solutions in the literature modified the beams in real time using their feedback as an input. The strategy my team ended up going with was using classical estimation techniques instead. So I will be reporting on one of the papers I looked at. Now, as a reinforcement learning approach, it does not require an online training phase and large data sets, and it can be easily adapted to different configurations. It does not require continuous inputs, which makes it not viable for the competition, unfortunately. So this is reconfigurable intelligent surface assisted multi-user MISO systems exploiting deep reinforcement learning. Reinforcement learning decides the best action to be taken given an environment. In this problem, the state is determined by the two beamforming matrices, the channel responses, and the sent and received power. The action is the configuration of the beamforming vectors, and the reward is the capacity of the channel. As the domain is very large, it is impossible to directly apply a search for the best policy, and a deep neural network is used instead to find the policy. Referring to the figure on the right, there are actually two neural networks, and the motivation for this is that simply training on the policy is not always reliable, and to compensate for this, after the action is selected, the Q function given the selected action is estimated, and it is used to weight the update equation of the policy. This algorithm is the critic actor algorithm. The actor-critic algorithm for reinforcement learning has an actor network, which outputs an action, and a critic network, which judges that action. In particular, the actor network uses a technique called policy gradient, which takes an input, in our case the state information, puts it through the policy, which is a neural net, and outputs an action. This action is sent through the critic neural network along with the state information and produces an estimation of the Q function. The training of the critic network can be seen below in the update equations and is called Q learning, where the loss is the mean square error of the Bellman equation minus its previous value, and its reward is the capacity of the channel. The policy is then updated, but as you can see, it uses both the gradient of the policy and of the Q function. The actor-critic algorithm was not designed for neural networks. One issue that arises from using them is that the loss function can vary each iteration. This can be minimized by creating a second set of parameters that are used to create target values and periodically updating them with the newest parameters. A second issue is that sequential inputs are highly correlated, which violates the assumption of independent data. To accommodate for this, buffer collects all the state transitions and actions, which can be combined later to train the network. Above is a diagram of the neural network architecture with the critic network on the left and the actor network on the right. They are both two hidden layer dense neural networks with a couple changes. The biggest change is the batch normalization after each hidden layer, which is necessary due to the high amounts of internal covariate shift due to the greatly changing parameters. The widening pre-filter is another way of reducing correlation. And finally, the activation function for the layers is the tanh, and it's also using the atom optimizer. The table on the right summarizes the hyperparameters. There's not much to note here other than the very high discount rate. The amount of parameters is not specified as it is dependent on the number of RIS elements and number of users. In general, though, RISs can have over 5,000 elements, meaning that the hidden layers can get very large. So now that we've gone over the neural net architecture, I'll recap the algorithm, but in general. So it loops over any number of channels and for a specified duration of time, which can be replaced with a convergence criteria. After providing the initial policy, the channel characteristics, and initial network parameters, for each iteration, the state is input into the actor neural network, which is the policy, and it suggests an action to take. The state and reward are then updated. Then, given the action, the critic neural network estimates a new Q function and the required gradients are calculated. Finally, the actor and critic networks are updated and it repeats until convergence. So after going over the implementation, I'll now briefly cover the results. So these were produced in a simulation and compared the method to two commonly used methods. It can be seen on the graph that in terms of the capacity, which is on the y-axis, the deep reinforcement learning method performs close to or better than its benchmarks. Furthermore, it matches these benchmarks over the number of elements and a number of users as well as the transmitted power. It is superior to these methods in that its implementation is straightforward relative to the more complex minimum mean squared error approach, meaning that it's more modular. It is also able to quickly learn its environment and adapt to it, and it requires less setup than other machine learning solutions. So that concludes my presentation. I hope that I was able to give a success story on using deep reinforcement learning for actual electrical engineering applications. The main paper I referenced, as well as the others I read for some understanding, are given below. Thank you.